Hello. In this video, we talk about event simulation analyses, their purpose, workflow, capabilities, and what results they produce. Event simulation produces results common to other structural analyses, such as displacements and various stresses. However, it is not limited to static conditions or elastic materials. Nonlinear material behavior is supported. Large deformations and free body motion are supported, as well as contact interactions that can change throughout the simulated event. Velocity and acceleration results are available. You can simulate part breakage through the automatic elimination of elements from the mesh at strains above a specified value. Event simulation is a fully dynamic analysis tool, taking into account mass, velocity, acceleration, damping, and inertial effects. As such, it is useful for analyzing impacts, forming operations, and many other dynamic events. This model is a two-part snap-fit assembly, and we simulate the insertion of one part into the other. The locking fingers deform as they're pressed into the middle hole of the stationary part. Contact allows the parts to slide along and separate from each other freely, but prevents penetration. Let's look at the process of setting up and solving the analysis. Create a new study, choosing the Event Simulation Analysis type. Then, click this icon to access the study settings. Let's set a total event duration of 6 milliseconds and choose to save 12 sets of incremental results. We'll define an absolute mesh size of 3 millimeters, which will produce two elements through the main body thickness of the two parts. We're not concerned about stresses in the stationary body, and we can reduce the solution time by specifying that this body is rigid. Stresses and strains are not computed for rigid bodies. Substitute a stronger material for the ABS plastic previously defined in the model workspace. We'll use nylon 6/6 for both parts. Apply a constraint to the stationary part. Notice that it is recognized as a rigid body, and 3 rotational degrees of freedom are supported in addition to the translational ones. We'll keep the default action, all degrees of freedom constrained. Apply a prescribed translation of 10 millimeters in the -z direction to the front face of the moving part. This translation pushes the parts together. Leave the X and Y components active too, but keep the magnitude at 0. This technique prevents X and Y motion without having to apply a separate fixed constraint. Define a multiplier curve to specify how the displacement varies over time during the simulated event. This curve decelerates the part as it approaches the fully inserted position for a smooth action. In the first 2 milliseconds, the part moves 6 millimeters, 0.6 times the translation magnitude of 10 millimeters. Therefore, the velocity during this period is 3,000 millimeters per second. We'll need this velocity in the next step. Next, we apply an initial linear velocity to the moving part. This action prevents the shock of instantaneously accelerating the part at the beginning of the event. Essentially, we're saying that the part is already in motion at the beginning of the simulation. The speed, as we've just determined, is -3,000 millimeters per second in the z direction. Automatically generate the contact sets. We'll keep the default global separation contact setting, but disable self-contact. We don't expect any part to deform enough to contact itself, and not checking for self-contact will shorten the solution time. Ensure that the Select Through option is enabled under Selection Filters. In the next step, we need to select hidden faces of the model. To provide smooth contact surfaces and a more accurate contact solution, we need a local mesh control in the contact regions. Also, a finer mesh all over the locking fingers will provide better stress results. Let's set the size at 1 millimeter, or 1/3 of the global mesh size. Select all of the faces of the locking fingers and the middle hole in the stationary part. Then apply the mesh control. The study is ready to solve. Event simulation studies must be solved in the cloud. When the solution finishes, the von Mises stress results appear. First, let's take a look at the mesh to see the local refinement we defined and hide the stationary part for a better view of the locking fingers. Now, take a look at the displacement results. We'll display a chart of this result versus time. Notice that the displacement curve matches the translation multiplier curve we defined during the study setup. We can create a slice plane for a better view of the part interaction and locking finger stresses. Choose a reference face and drag the slice plane to the desired location. You can also specify an exact offset. Here, an offset of 6.35 millimeters places the slice plane in the exact center of the part. From the browser, hide the slice plane so that it doesn't obscure the contour plot. We're interested in the bending stresses in the locking fingers to make sure they won't break due to excess stress during assembly. The normal ZZ stress tensor represents the bending stresses in the fingers. Drag the step slider to see how the stresses vary during the event. Finally, animate this result to watch the entire insertion event. There are 13 steps, one being the initial condition, plus 12 calculated steps. A setting of 26 steps here gives us 2 animation frames per step. Notice how the fingers oscillate in the last millisecond of the event after they snap into place. Analysis of many such assembly, disassembly, impact, and deformation events is possible using event simulation. Thank you for watching.